This is Euclid Book 10, proposition number 49. And here's the illustration. We have two lines. This one's AB and it's cut by C. This is line EG and it's cut by F. This line here is line D and this one's H. Okay. Now then. Alright. What does this one say? It says to find the second binomial straight line. Let two numbers AC, CB be set out such that the sum of them, AB, has to BC the ratio which a square number has to a square number. Now let's stop that right here. Alright. What's AC and CB? Well, this is AC right here. This is CB right here. And the sum of these two happens to be the line AB. That's what Euclid was saying. Okay. So now we have that. Now, as AB is to BC, okay, so as AB is to BC, so as a square number is to a square number. Okay. But AB does not have to AC, okay? So if we made a ratio of AB to AC, that ratio would not have a ratio identical to a square number to a square number. Let a rational straight line D be set out, and let EF be commensurable in length with D. Okay. So, EF, right here, is commensurable in length with D. Okay. So far, so good. Therefore, EF is rational. Okay, so now we're going to say that this length right here is rational. Okay, let's go on. Let it be contrived then that as the number CA is to AB, so also is the square on EF to the square on FG. This is by Euclid Book 6, I'm sorry, this is by Euclid Book 10, proposition number 6, porism. So, as CA is to AB, so now we got a ratio. We're going to start a ratio. As CA is to AB, that's the first part of your ratio. The second part of your ratio is this. The square on EF to the square on FG. Okay? So now we're going to say that we're going to take EF here and we're going to form a physical square. Okay? That means that all four sides of that square are going to be the length of EF. Then we're going to form another square and it's going to be FG. And all four sides of that square are going to be the length of FG. So, what's the ratio? As AC is to AB, as AC is to AB, so is the square on EF is to the square on FG. Okay? Remember, it's not EF and FG that's the ratio, it's the square on EF to the square on FG. Those are those two squares I told you to draw. Okay. So in other words, you have the square area of EF and the square area of FG. And that's the other half of your ratio. Alright. Let's go on here. Therefore, the square on EF is commensurable with the square on FG, which is by Euclid Book 10, proposition number 6. Therefore, FG is also rational. So now we're going to say that this length right here is rational. Okay. Now, since the number AC has not to AB the ratio which a square number has to a square number, neither has the square on EF to the square on FG the ratio which a square number has to a square number. Therefore, EF is incommensurable in length with FG, and this is by Euclid Book 10, proposition number 9. So, this is incommensurable with this. Okay. Therefore, EF and FG are rational straight lines commensurable in square only. Therefore, EG is a binomial. That's by Euclid Book 10, proposition number 36. Okay, so we now know that this length right here is a binomial. Okay. It is next to be proved that it is also a second binomial straight line. For since inversely as the number AB is to AC, so is the square on FG is to the square on EF. Let me write this out for you. You're going to need this. That's what he's saying right there. Okay? That's what he's saying. Okay. Okay. Now then. Well, AB is greater than AC. Well, obviously, the length of AB is greater than the length of AC. We know that. Okay. Therefore, the square on FG is greater than the square on EF. Okay. So this is bigger than this. This area is bigger than this area. We got it. Let the squares on EF and H be equal to the square on FG. Okay. So what happens here is we're going to draw another square. Okay. And that square is going to be H. What you're going to do is you're going to take the length of H and you're going to make a square out of it. All four sides of that square are going to be the length of H. Then what you're going to do is you're going to add the area in EF square to the area in H square, and when you add those two areas together, then you get the same area as the area of the square on FG. Remember that square we drew with the length of FG? Okay, so this area plus this area equals this area. Okay. Therefore, convertendo, as AB is to BC, so is the square on FG to the square on H. So now we're going to just change the equation just a little bit. Okay, so now the equation looks like this. Alright, so what we're saying here is as AB is this length is to BC, so is the square on FG is to the square on H. Okay. And this is by Euclid Book 5, proposition number 19, porism. But AB has to BC the ratio which a square number has to a square number. Therefore, the square on FG also has to the square on H the ratio which a square number has to a square number. Therefore, FG is commensurable in length with H. This is by Euclid Book 10, proposition number 9. So this line is commensurable in length with this line. Okay. So that the square on FG is greater than the square on EF by the square on a straight line commensurable with FG. Okay. So the area of this is larger than the area of this, and how much larger this is to that is this area right here. Okay. Now we got all that. And FG and EF are rational straight lines commensurable in square only, and EF, the lesser term, is commensurable in length with the rational straight line D set out. Therefore, EG is a second binomial straight line. Okay. So now, after saying all that stuff, this line here is a second binomial. And thus ends the proof. I will tell you more in a future video. Stay tuned.